Welcome to this lesson on telescopes. Telescopes are fascinating optical instruments that allow us to view distant objects in space. In this video, we'll explore two main types of telescope designs: refracting telescopes and reflecting telescopes. By the end, you'll understand how each type works and what makes them different from each other. A telescope is an optical instrument that collects and focuses light to magnify distant objects. The key principle behind telescopes is that they use either lenses or mirrors to gather light from faraway sources. This collected light is then focused to create a magnified image, making distant objects appear closer and brighter than they would to the naked eye. Whether we're observing planets, stars, or galaxies, telescopes help us see details that would otherwise be invisible. Let's begin with the refracting telescope, also called a refractor. This type of telescope uses lenses to bend and focus light. A refractor has two main components. First is the objective lens, which is the large lens at the front of the telescope. It collects incoming light and forms an image. Second is the eyepiece lens, which is the smaller lens you look through. The eyepiece magnifies the image formed by the objective lens, allowing you to see distant objects in greater detail. Here's how a refracting telescope works step by step. First, light from a distant object enters the objective lens at the front of the telescope. Second, the objective lens refracts, or bends, this light and converges it toward a focal point. Third, at the focal plane, a real inverted image is formed. This means the image is upside down compared to the actual object. Finally, the eyepiece lens magnifies this inverted image, making it large enough for your eye to see clearly. The process relies entirely on the refraction of light through curved glass lenses. Now let's look at the reflecting telescope, commonly called a reflector. Unlike refractors, reflecting telescopes use mirrors to reflect and focus light instead of lenses. A reflector has two main components. The primary mirror is a large curved mirror at the bottom of the telescope tube. It collects incoming light and reflects it back up the tube. The secondary mirror is a smaller mirror positioned near the top of the tube. It redirects the focused light to the side of the tube, where the eyepiece is located. The working of a reflecting telescope follows these steps. First, light from a distant object enters the open tube of the telescope. Second, the primary mirror at the base reflects this light and focuses it back up the tube toward the secondary mirror. Third, the secondary mirror redirects the focused light to the side of the tube, sending it toward the eyepiece. Finally, the eyepiece magnifies the focused image for viewing. Because reflectors use mirrors instead of lenses, they avoid certain optical problems that can occur with glass lenses. There are several common designs of reflecting telescopes, each with unique features. The Newtonian design uses a flat secondary mirror positioned at a 45-degree angle. This mirror directs light to a side-mounted eyepiece. The Cassegrain design uses a convex secondary mirror that reflects light back through a hole in the center of the primary mirror. The Gregorian design is similar, but uses a concave secondary mirror, which produces an upright image through the central hole. Finally, the Dobsonian is essentially a Newtonian telescope mounted on a simple altitude azimuth mount, making it very easy to use and popular among amateur astronomers. Let's compare refracting and reflecting telescopes. Refractors have several advantages. They feature a sealed tube design that requires low maintenance and protects the optics from dust. They produce sharp, high-contrast images, making them excellent for observing planets and the moon in fine detail. On the other hand, reflectors also have distinct advantages. They can be built with much larger apertures at a lower cost compared to refractors. They don't suffer from chromatic aberration, which is a color distortion that can affect lenses. And their larger apertures make them better suited for observing faint deep sky objects like galaxies and nebulae. Each type has its strengths, and the choice depends on what you want to observe.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.